Okay, so welcome to a talk on multimodal neuroimaging overview. I will say I'm Pete Molfese. I'll be your sort of wild ride coordinator today. And there we go. So I'm part of the fMRI core facility, but I also serve as the scientific lead for this Center for Multimodal Neuroimaging here at NIH. And someone said, well, can you put everything that you do in one slide? And I said, wow, not only does it fit in one slide, it's somewhat of a colorful slide. So we do kind of three main things. We manage all of the simultaneous EEG fMRI equipment. We help people put together data from different multimodal tools like EEG, fMRI, PET, MEG. And we run yearly workshops. So in the past, we've run workshops on multimodal neuroimaging, naturalistic stimuli. This year, we actually have an eye tracking workshop that's going to be September 4th and 5th. So hopefully come by and see that. And then in the future, we're planning one on layers. So first of all, why this talk? That I think is partially that the talk title was given to us. And so I was like, well, that is the talk title. I will try to fit something in. And more importantly, this talk is back-to-back with another talk that I'm giving on Tuesday. So if you like this talk, come back with, fresh rotten fruit for next time. On Tuesday, I'm going to be talking about EEG with and without simultaneous fMRI. So you can see that there's potentially a decent amount of overlap between those two. So what I thought I would do is I'd take today and talk mostly about theory, and by that I mean kind of like the higher level forest instead of the trees. And then next week, I'll talk a little bit more about applications with demos on how you might clean your EEG data if you're collecting simultaneously with fMRI, and sort of how those apply to other techniques as well. And specifically next week, I'll also be trying to focus a lot of the conversation on how to do EEG fMRI at NIH. So what tools that we have available, and we've kind of replicated this throughout the summer course with some of the other talks on MRI. So as a general overview today, I'm going to talk about what multimodal neuroimaging is, kind of motivation, and the main themes that I'd like you to walk away with are doing multimodal neuroimaging is hard, and doing multimodal neuroimaging is certainly important and well worth it. So we'll kind of break it down like that. Okay, so multimodal neuroimaging. Well, it's neuroimaging that has multiple modals. So anything that you could put together, fMRI, EEG, MEG, EEG, fMRI and structural MRI, fMRI and DTI, so on and so forth. There's a long list. And the main reason for doing multimodal neuroimaging is to try to play to these trade-offs, mostly in temporal and spatial domains. So this figure, nicely updated in 2014, you can see the old one here from 1988 with many fewer modalities, is that here along the x-axis, we have time, temporal domain, and here on the y, we have the spatial domain. And you can see that EEG and MEG are pretty good at getting to does it happen in the brain? Does it happen on a particular lobe? Or does it sort of go into a map? So centimeters of resolution. Whereas fMRI is considerably slower, but we can get down to the layers of the brain, feed-forward and feedback models, things like that. And so the idea is that if you put together any two or more of these modalities, you might be able to collect complementary data that give you things like when in the brain and where in the brain. And that was sort of the initial impetus. But at that point, we were still talking about 2 or 3 electrodes or only a handful of sensors. Whereas now we're talking about hundreds of sensors in every single domain. And so now we can start to put techniques together to improve the quality in either the temporal or the spatial, and oftentimes both. So multimodal possibilities are many. I've kind of highlighted them here as green as easily possible. So things like simultaneous EEG, MEG, EEG fMRI, EEG PETs, and EEG TMS, like neuromodulation. And then some things that are not currently possible, like you can't really have an MEG inside of an MRI, although I'm sure someday someone will figure that out. And you can't do things like DTI and EEG together because you end up heating up the EEG electrodes. But I think a lot of the times when we start thinking about multimodal, we get constrained into these, like, these are the only things that are possible, the only things in green. But it turns out if you don't care about whether or not these data are simultaneous, suddenly the sky is the limit. Like, everything is possible. And there are motivations where you might want to do them simultaneously, and I'll talk about those. But there are also plenty of times where you're just like, hey, I have the same subjects or even sometimes different subjects on these data. Is there converging evidence across modalities that might give me an insight into how the brain works? Or just, the average mind of the typical college student. A lot of what I talk about with multimodal comes down to trade-offs. There are sometimes monetary trade-offs. Some things are expensive, some things are cheap. You cannot currently buy any neuroimaging equipment at Claire's, if Claire's is still a thing. Sometimes it's technological trade-offs, like sometimes it's easy to do something, sometimes it's hard to do something. Sometimes it's modality trade-offs, like how would you do, say, experiment X in this kind of modality? Or could you even do something where you're interrupting the brain in a particular way and then combine it with some kind of recording? Most people immediately reach for the informational trade-offs. So as I alluded to before, you could use something like EEG or ERPs and say, okay, when in the brain are things happening? And EEG, ERPs are really good at doing that. Say, identifying that faces are kind of identified at about 170 milliseconds after being seen and encoded as faces specifically. And then fMRI gives you kind of a where in the brain. These are kind of the glossing over moments. But you can see here, here's a N170 to a face, and here's an sort of fusiform face area activation in MRI. Same experiment, same subject. But we can also ask questions on, okay, what happens if I use, say, TMS to zap a particular area of my brain and interrupt the flow of processing? Like, can I use that in combination with these techniques? Absolutely, and that might get at interesting research questions that can only be done with multimodal imaging. I want to give a few examples just to put some concreteness to this. So here's kind of a very classic, and I know it's a very old paper, but it's classic for a reason. Devner in 2005 did a set of kind of separate experiments, EEG and fMRI, and were able to show in this flanker task where you either say, you have to push a button that indicates the direction of this middle arrow. And sometimes it's easy because all the arrows are going in one direction, congruent. Sometimes it's hard. The middle arrow is going in the opposite direction, incongruent. It's a lot of interference that happens. And what they showed is that in the EEG, you can pick up on those differences between congruent and incongruent fairly easily. And it happens right around 250 or so milliseconds. And that if you source localize that in the brain using just an equivalent single dipole, which is relatively easy mathematically, you find that your activation is right around the anterior cingulate. Same experiment in fMRI, find out that lo and behold, we also see this anterior cingulate activation. Pretty clean, same experiment, different modalities, you find out the same thing, you get this added benefit. That's kind of the baseline where we want to be, right? Like we want this converging evidence. Same thing can be said about EEG and MEG. And you might say, well, EEG and MEG are kind of similar or very, very similar. It turns out that they are similar in many, many ways, but they do have different sensitivity profiles, so to speak. So here is that same flanker task in MEG at the top and EEG at the bottom. These are evoked averages. And it's important to say or note that EEG picks up on sort of all of the sources. I'm doing air quotes for people. Oh, I guess you can see me on the camera. All of the sources, including radial sources in the brain, but it has lower SNR than MEG. And you do get some signal smearing. So as the electrical current from the brain kind of leaks out, it goes through other parts of the brain, and then the CSF, and the skull, and the scalp, and whatever else happens to be around. MEG, in contrast, doesn't pick up on all of the sources that happen in the brain, and we will say it's most sensitive to tangential sources, so sources that kind of like exit the head, go through a magnetometer or gradiometer, and are picked up that way. MEG does have higher signal to noise, but there are some trade-offs there. So in EEG, we have our electrodes directly on the skull or on the scalp, and in MEG, the sort of helmet is kind of floating. So your proximity to any particular side of things may vary. But importantly, because I really want to emphasize this, these are complementary. And so not only can you put them together, you can put them together and get better results, like better source analysis. And it's not just better source analysis because you have more sensors. Say you have 256 electrodes and 268 magnetometers. It's actually better by combining it because you're getting those two different types of information and putting those together to improve your source localization. Yeah.
Just a question of your previous slide. My understanding is that EEG is also only susceptible to dipoles that are oriented in a certain, axis.
Yeah. Most people will say radial sources.
Right.
Yeah.
How does that relate to the sensitivity of EEG versus MEG?
So
when you count that.
Yep. Yeah, so there are more radial sources than there are tangential sources. But the trade-off is that even if you have a radial source, the idea is that that source may not be sort of exposed closest to whatever electrode you're in, but it will be exposed somewhere on the head because it's going to kind of leak voltage somewhere. And that is the trade-off, is you are getting more information, but it's going to be noisier information, sometimes too much information. Yeah, I will talk about dipoles on Tuesday and sort of how they map in terms of the scalp and how you can kind of see them as sort of double-ended flashlights where you see positive voltage and negative voltage and how those get moved. You can also put together, say, fMRI and diffusion. So you can use fMRI results, say, in this case, in the default mode network, as your seeds for doing probabilistic tractography in DTI. And then you can come up with some kind of way of saying, okay, how do these tractographies or how do these bundles of white matter tracks correlate with different behavioral mechanisms? In this case, these folks found that memory scores were correlated both with global and local efficiency in the DMN, but they also built this really nice graph theory model based on the tractography to identify where that was true and where that wasn't true. You can also do things with fMRI and magnetic resonance spectroscopy. So here they had typical struggling adult readers, and they found that GABA in the left IFG, one of our main reading areas, predicts real-world reading behavior, but only if there's sufficient kind of resting state functional connectivity between different reading areas. And it turns out that this is only true if you have a particular level of GABA at the time. As I said, a lot of things are about trade-offs. So just to kind of take the big three, or yeah, I could probably expand this to be the big six at this point. There are pros and cons for each of these techniques. So EEG, for instance, EEG and MEG both have very high temporal resolution. EEG tends to have lower spatial resolution, but especially than MEG, but EEG is very cheap. You can build an EEG system yourself for a little bit less than $1,000 per channel. If you want to do a research grade system, you want to go to Radio Shack doesn't exist anymore, but if you want to go to your local hardware and make something that's consumer edge or that competes with the consumer EEG, you can do that for about $250 per channel. There are YouTube channels that will teach you how to build your own EEG system. Your mileage may vary. In contrast to EEG and MEG, fMRI has great spatial resolution, but just like MEG, it's very expensive. You're not going to be, say, ordering an MRI machine for your home or possibly taking an MRI machine home with you. If you do see me after class, we have a lot to talk about. So this slide should give it away. It's written in big, bold words. Doing multimodal is hard, and it's hard in three kind of areas. It's hard for how you design things, how you analyze the data, and how you interpret the data after the fact. So on design, oftentimes if you're sitting down and you're saying like, I want to design my own multimodal study, it requires you to have some domain knowledge on the thing that you're studying, right? Like you're not going to wake up tomorrow and be like, you know what, I'm going to study reading development when you don't have any domain expertise in reading, right? Or language. Probably not going to happen. Not going to say it never happens, but unlikely. It also requires that you have some kind of domain knowledge or expertise in whatever techniques you are using. So you're probably not going to be an EEG person and be like, you know what, fMRI seems super easy. I'm going to do that tomorrow without talking to a few people. And it also requires the technical knowledge to carry out at least some portion of the experiment, because as more and more science is transitioning from sort of solo sports into team sports, you're going to need to bring some kind of expertise to whatever your research team is. So if you were starting out today, and Dan Handwerker did an awesome, like if you were starting an fMRI experiment tomorrow, like these are kind of overlapping questions. So if you're designing a multimodal experiment, do you have the equipment? You can't do simultaneous EEG MRI if you don't have either EEG or MRI, hopefully both. Do you have the expertise to operate that equipment? Is it worthwhile? So is the thing that you're studying shown in at least one of those modalities? If you're like, hey, I'm going to study this thing for the first time, it's never been correctly imaged in any kind of neuroimaging technique, multimodal may not be the first thing that you reach for to say like, aha, I'm going to just try to collect as much data. I know that for people who know me, I will often say more data is always better. I advocate for turning the eye tracker on anytime you have someone in front of a screen. But more data, particularly at cost, is not always better. And then the final question is, can you do this well? Can this be an experiment where your data quality is going to be exceptional? So just to add on, for design, the questions are, what is the value added for doing multimodal? And does it have to be simultaneous? Those are really the biggest things. If it doesn't have to be multimodal, then tune in for the other talks. If it doesn't have to be simultaneous, we've got a lot to talk about. Simultaneous, really? So a lot of data can be inferred from simultaneous. You have the benefits of your participant being in the experiment for the first time. So it's the first time the person's seeing the experiment, you get the same information across different modalities as they're going through the task at once. It's not, oh, we're going to counterbalance the visits, or, oh, we're going to counterbalance our individuals. Like, you are getting data that is converging on the same participants at the same time. You can do things like look at individual trial modulation. And Adrian Gilmore has been doing this with naming things inside the scanner with EEG MRI. And you can look at things like the coherence and resting state relationships between networks that we measure in BOLD and networks that we measure in EEG. This is particularly nice if you want to do things like dynamic causal modeling, because it's often been said that DCM lends itself quite well to high temporal resolution things like EEG. So our questions for design or data analysis is, are there going to be artifacts that you need to take care of if you're collecting simultaneously? Can you fix those artifacts? Sometimes the answer is no, but as I'm going to show you, often the answer is yes, or you can learn to live with them. So for instance, in simultaneous EEG fMRI, if we collect EEG data inside the scanner, we get these large gradient artifacts, and they look like this. And as I said, they're caused by the gradients. We also get this second artifact called the ballistiocardiogram, or BCG for short. And this is caused by movements of the electrodes inside the scanner. So if you think of kind of the fleshy or squishy part of your face, you have electrodes there, but you also have a little bit of squish in the rest of your head. Every time your heart beats inside the scanner, the electrodes move just a little bit, and that causes an inductive charge, just like your Sonicare toothbrush. And that sort of little bit of movement causes the electrodes to also pick up on artifacts. That was a fun transition. So you can remove both of these, or you can kind of learn to deal with them in useful ways. For gradient artifacts, they're pretty straightforward. We just take a template of what that gradient artifact looks like as we measure it over time, and then we just subtract that template over all of your EEG signal, and you go from this kind of raw signal to your mostly EEG looking thing here. And with BCG artifacts, we know that those electrodes move whenever your heart beats. And so all we need to do is measure when your heart beats and then go out about 200 or so milliseconds afterwards when your face shows that pulse artifact and say, hey, like, here's where the artifact happens. We know temporally where it is, and we can use either PCA or ICA to isolate it and then subtract it out. Again, neither of these are absolutely perfect, but they do make your data much more manageable for doing simultaneous. Yeah.
Presumably, the electrodes are moving in a behavioral setting.
Yep.
So it's basically what the Earth's magnetic field is strong enough to drive some sort of change in the signal with those movements of electrodes.
Yeah, so the question is why does this artifact only happen in MRI? And yes, it's that you have a very strong magnetic field and you're moving an electrode inside that magnetic field that causes a charge.
Is there any implications about doing simultaneous in higher fields in this regard, that the artifact is more pronounced and more challenging to deal with?
Yep. To repeat the question, does this artifact scale with MR field strength? Absolutely. It scales linearly with field strength. Actually, yeah, pretty sure it's linearly. And so it is smaller at 1.5T. It's pretty manageable at 3, and then at 7T, Laura Lewis has been doing a bunch of work on how to measure it appropriately and then subtract it out, but it is big. Turns out that carbon loops are often the answer, and I'll talk about that hopefully on Tuesday. Haven't made that slide yet. Okay, additional questions for data analysis are, how will you combine the data? So you can take out the artifacts all you want, but if you're just at the end of the day going to be like, okay, I've got like my file drawer of behavioral data, and I've got my computer that's my EEG computer, and I've got my computer that's my MRI computer, like, how am I going to make sense of those? Am I just going to pull up all of the data and then like stare at it? And maybe it'll do the interocular traumatic test of significance. That's where the results leap off the page, hit you squarely between the eyes. Probably not. That doesn't publish terribly well. So the ways that we typically do this is that we need to co-register our data across the modalities. And we can do that using either like co-registration of sensors, building head models, if you're doing like MEG, EEG, and you have a structural MRI, and coming up with ways of modeling sources. In this case, I wrote EEG sources, but it could be many, many things. So just to put things in context, for EEG, although you can also do this with OPMs, with fMRIs, whatnot, you can take pictures of the head. So you can take pictures with an iPhone. There are a couple of groups out there that have allowed you to just wave your iPhone at people and get kind of okay sensor registration. This system has 12 cameras and will register within a couple of microns each electrode. That might be slightly overkill. But you can see that it takes 12 pictures of the head, and then this is all of the sensors marked on my head, and then this is sort of the 3D model of all of the sensors in 3D space. So then I can line those sensors up with your MRI, and then I can have a little bit better of a sense of, okay, where were these voltages picked up in relation to the brain? Also in EEG and MEG, I can build different head models to represent how the electrical currents may get from wherever they originate from, and then to whatever the sensors are. And we have simple models like shell models where we just have different spheres, whether those are like brain, CSF, skull, or scalp. I've also seen 3-sphere models where we take out one of those. Or we can do things with like finite difference models or finite element models where we model every voxel in the brain as gray matter, white matter, or a percentage of each, and then we give it a resistance factor. And then that can sort of tell you, like, given any given voxel, like, what is the probability that the voltage you're seeing is from that particular part of the brain. But it's not all sunshine. I feel like I'm giving you a very realistic, but maybe a Debbie Downer look at multimodal. It is kind of cool that you can then do things where you combine the methods and you get fusiform activation in both fMRI and EEG. But the other caveat here is that with fMRI, we get sort of this gamma function, and it's area under the curve from that gamma function usually. And you can say, okay, like, this is the activation in MRI. This is my one map in MRI. But in EEG, we actually get a sort of moving voltages across the scalp that are represented down here. And you might have to say, like, when in the brain does this particular map happen? So like, when in the brain is the thing that I want to detect happening? And then you can go to that point, and then you can look at your source map for that point, and maybe it matches up, maybe it doesn't. There are ways of dealing with this. Again, I'm going to talk about this more on Tuesday. This is just to give you a sampling of like challenging ways that multimodal data ends up getting put together. And this brings us to our other or last category of like multimodal is hard, which is interpretation. So how do you interpret your findings? Do you analyze the data and make generalizations? Do you just say like, I collected a whole bunch of MRI data, or someone else collected a bunch of MR data, someone collected a bunch of EEG data, I'm going to relate them myself? And what does it all really mean? Which I feel like I could teach a semester-long course on. Okay, that's a lot of doom and gloom to say. There is actually some really great news. We're making incredible progress, and not just we here, but like across the entire field. Everyone is making incredible progress in combining different modalities, whether it's simultaneously or not simultaneously. Simultaneous methods are absolutely improving how we remove artifacts and also how good the quality of the data is before we even get to the artifacts. So if you have artifacts on top of bad data, it's going to be almost impossible. If you have artifacts on top of amazing data, it's going to be better than artifacts on top of just kind of average data. And non-concurrent methods continue to improve through integration and mostly the efforts of open source software. So incredible pushes in open source EEG, MEG, fMRI software, whether it's, I'm going to leave them out, many of them out, like M&E, Field Trip, Brainstorm. Obviously, AFME has some tools for doing this. Some of the other groups also have things for doing this. It is a moving target, but if you are collecting multimodal data today, you're likely going to get better results than if you collected it even 5 years ago. And I will say the reason that you sat through this is that multimodal is important. So it provides hopefully complementary and overlapping information. But in the case that I showed you with the simultaneous EEG, MEG, we get improved source localization, not just because we have a combined set of sensors, but because we have complementary data types coming in. It hopefully, and actually I know it does, provides better studies of individual differences because they don't always move in the same way. So I may get 2 participants who give me EEG and MRI data, and their data combine to look somewhat similarly, but they combine in different ways. And so we see a lot of hemisphere effects that give us kind of similar results across the two. But when you look at it, sometimes it's about the timing of the EEG compared to the MRI. And if multimodal data really does allow us for these creations of latent variable models in order to put in an oversimplified way, EEG, MRI, and TMS together, which is kind of our current goal, and so on and so forth. Going to leave you with open questions. I promise these aren't really cliffhangers for Tuesday, but sort of. So our open questions with multimodal are, what questions best lend themselves to multimodal neuroimaging? Sometimes you don't need to do multimodal. In fact, sometimes you don't even need to do imaging. About once a year, someone writes a popular press article that says, we've got it, you can go lay inside the MRI, and we can tell you whether or not you have dyslexia. And it's like, cool, yeah, we can do that, but we can also do that with paper and pencil tests, or sometimes just by like watching someone struggle how to read a book. You don't always need multimodal, you don't always need imaging. We do have to say, like, how should we standardize multimodal analyses? And there's been a lot of work in the BIDS community for standardizing, say, MRI analyses. There's been a lot less in the EEG and MEG side, although the MegCore here has done some amazing work with magnets and various other tools for standardizing across site data collection and analysis. And we also have to start asking in our publications and reviews, like, how can we hold authors to a particular standard to say, is this real or not? Did we really need multimodal to tell us this? And at the end of the day, is this interpretation correct between the two modalities? And with that, I'll take any questions. As I said, I'm part of the fMRI core facility, and special thanks to my emotional support dog, Belle, my parents, and of course, remembering Sean Merritt. If it was easy, everyone would be doing it, right? Any questions?
Yeah. With EEG, you're running electrical signals kind of over the cloud as they're heading away. Are those detectable in EEG when you're doing simultaneous studies?
In terms of blinks, things like that?
No, I was actually thinking like, can you actually kind of pick up through the MEG what the EEG signals are just because you're putting wires inside of an MEG system?
So the wires, at least currently, don't cause us any problems for being inside the MEG system as long as they're shielded. The cascading electrical currents, like if you have like a blink or something like that, that is much more a problem in EEG. Like in general, like artifacts, like muscle artifacts are a lot more of a problem in the EEG than in the MEG. Yeah, did I fully answer your question? Anyone else? Yeah.
Just curious, does EEG and fMRI have some correlation information? Like if you measure EEG, will it be compared with fMRI in simple function?
Okay, so let me see if I can repeat the question. Is there a correlation between EEG and fMRI? Like if you measure them simultaneously, should you get kind of converging information?
Yeah.
Yep, absolutely. So if you, I showed a couple of slides from an face house perception study where we see converging evidence for EEG for fusiform if we source localize at 170 milliseconds when we know that kind of face processing happens. And then also in fMRI for the exact same study, we see, again, fusiform information. Obviously, it happens slower in fMRI because blood flow is slow, but there is nice convergence. Sometimes there's also nice divergence, and that is one of those things like, what do we do when they don't necessarily line up? There's been often a call for people to come up with studies where they measure EEG and fMRI at the same time, and the hope would be that you could like take every bold activation and get an EEG scalp topography out of it. And this comes up, I'd say about every 5 years. Someone says, let's make an encyclopedia of all of the EEG scalp topographies and how they relate to bold source activation. And that turns out to be pretty impossible. And it's not impossible from the sense of like, it's easy to make a lookup table. It's impossible because EEG and fMRI are fundamentally measuring different things. Like fMRI is giving you the blood flow response, particularly like how the oxygenation level changes, whereas EEG is measuring the actual neuronal process, so the electrical currents. And it could be that you have times where parts of the brain are active and bold doesn't pick it up, and you could have times where EEG doesn't pick it up just based on how large the dipole is or other things that are going on.